Good morning, everybody. And I've already jumped into the course calendar because I am going to go down to Notebook 14. So if you scroll down here into the week 10 area, you'll be able to see Notebook 14, which is about one sample t-tests. Okay, so this is what we're going to be talking about. So let me kind of give you the outline for every hypothesis test. Okay, so we start with our null hypothesis. So our null hypothesis is an H with a subscript 0. And we also have the alternative hypothesis. What's true if the null is not? Okay, so in the lady tasting tea example, right, the null hypothesis was just random guessing. Right, we said that we calculated a probability of what it would be, what the chances would be if Dr. Muriel Bristol was guessing. And it turned out she got all 8 out of 8 correct, which was far less than a 1% chance of happening if she was randomly guessing. So we rejected the null, right? This was our statistical conclusion of reject the null. Why did we reject the null? Well, we calculated the p-value, and the p-value was far less than 1%. So I'll just put less than 0.01. And the p-value, after we do this probability experiment and calculate the p-value, the p-value is the probability that the null hypothesis is true. Well, Ron Fisher decided that the random guessing, was very unlikely to be true. So he rejects it in favor of the alternative, which was that Dr. Muriel Bristol could actually taste the difference in the tea. So that's how these hypothesis tests goes. We have a hypothesis. The null hypothesis tells us the probability experiment that we're going to run. We run the probability experiment, and the key thing that happens is we calculate a p-value, and the p-value is the probability that the null is true. Then, based on p, we either reject the null or fail to reject the null. So there are two statistical conclusions. We either reject the null or fail to reject the null. And we base that all upon whether or not p is less than alpha. And by the way, I've said this before, but I'll say it several times. Alpha, the standard alpha is 0.05. When in doubt, alpha equals 0.05. There are reasons to set it a little bit differently in certain cases, but this is an elementary stats course, and you'll be told what alpha is, and like I said, most of the time we will use alpha equals 0.05. So the very simplest hypothesis test is the one sample t-test. Okay, so that's why we're going to start learning right there. And let me point out a couple of things, right? It noticed that it says that we're going to use the scipy.stats module, okay? And we're going to import this test from SciPy, and we're going to call it t-test. So we're going to learn how to run a t-test, and we're going to call it t-test. That's how we're importing it. And you'll see that in just a moment. So you'll see that, in the initialization block. Boom. And you'll see, what are we doing? Well, this part defines a function called favstats that we'll use. But here's the part that is importing the SciPy, okay? And you can see the part up here that's importing the t-test. And it's also importing t, okay? And those are, again, just these t-test tools that we're going to use in this notebook. Now this is interesting. I'm sure you're thinking, what the Sam Hill am I supposed to get out of this picture? Okay, so in green is the t-distribution, in red is the bell curve, the standard bell curve. Okay, and notice that as this df slider, as it gets smaller, the green graph becomes a little shorter, and wider. But as degrees of freedom gets large, it gets very, very close to the standard bell curve. And that's exactly what you're supposed to get out of this. Sorry. That's exactly what you're supposed to see. And you can read this, but basically as the degrees of freedom increase, the distribution converges to the standard normal. And normal, this word normal, in statistics, it means bell-shaped. It means the bell curve, okay? And so it turns out that in all of these situations where we expect bell-shaped data, we end up using the t-test. And that's based on the t-distribution. So in this notebook, we have 3 hypothesis tests for our examples. And the first one is, do students take 5 classes per semester on average? Okay, so let's think about this in terms of the null and alternative hypothesis, all right? So to complete a bachelor's in 4 years without summers, a student must average 15 credit hours per semester, and most classes are about 3 credit hours, so this is an average of 5 classes a semester. Okay, so I'm just going to say that our null hypothesis, right, and this is a colon, so h with a subscript 0 and then a colon and then a mu equals 5. Okay, so we're just going to assume until we have further evidence, right, that the average number of courses taken by the students at UNG is 5. Okay, so that's our null hypothesis. Our alternative hypothesis is one of 3 possibilities. So let's scroll down here. I'll come back and do these code blocks in just a second. I will show you that there is just this table, right, based, and this should pull the data into the notebook so we can use it. And what is the test doing? Well, notice that the null hypothesis is an h subscript 0, and it says mu equals mu sub 0. What's the mu sub 0? Well, in our instance, right, that's just the number 5, right? And the alternative has to be one of these 3. Either mu is not equal to 5, or mu is less than 5, or mu is greater than 5. Now, what did we say? Well, we're just checking to see if it's 5 or if it's something different, okay? So the alternative hypothesis is mu not equal to 5. Is there some other number? Is it either higher than 5 or lower than 5? Is it different than 5? That is the question we are asking. Okay, and full disclosure, we won't be doing a lot of this manually, almost ever, right? But they are going to show us, you know, where the computations come from, what the computer is doing. All right, so we have this table, and this is favstats, which is a summary. It shows the 5-number summary. So we know the minimum number of courses that these college students are taking. There's a college student or some number of college students who took only 2 classes in a semester. And then there's some crazy person who is taking 9 classes, right? So we have a minimum of 2, a maximum of 9. The median is 5, and the mean is close to 5, but notice a little bigger. Okay, so we're finding out that 5 on average seems to be a good number. Here's the hypothesis test, and let's talk about it, right? So it's going into the classes table and dot column. In other words, we need arrays. We need an array to stuff in here. So instead of dot select, it's dot column. And then we point it at num courses. And then what's this pop mean equals 5? That's basically where the computer learns that our null hypothesis is mu equals 5. Remember I said that the null hypothesis is what determines the probability experiment? So we have to let the computer know, hey, population mean is 5, mu equals 5. That's the null hypothesis that we need you to calculate the p-value for. And it does. Sorry, skipped a little forward, but notice that we have test statistics. So this is the t statistic value of the 0.41465. Okay, and here's the p-value. But notice the p-value is 0.68, right? So p equals 0.68. I mean, I know that's rounded and it's got a lot more decimal places, but that's enough to show that that is greater than 0.05. Okay, and I will slip back to the PowerPoint. Remember that our rejection criteria is if p is less than alpha, we reject the null. Otherwise, we fail to reject it. So here we're in this case where we fail to reject the null. In other words, we conclude that the null is reasonably likely. So let's jump back into the notebook. And that's essentially what I just said. That's what this cell is going to tell you. We already talked about the null and alternative hypothesis. And they're showing you a formula here for how the test statistic is calculated. Okay. And it's based on the sample mean and mu sub 0. Remember, that's equal to 5. I kind of messed up there. The mu sub 0 equals 5. The standard deviation from the sample and the sample size. So knowing the average and the standard deviation and the sample size, we can calculate the test statistic and we can find out p. We can find out this p-value. Well, the p-value was large, right? The p-value was large. So what do we know? And here we get out into the reporting out area, right? So yes, this, I already showed you this. We already saw the code block where we found that out, okay? But based on a p-value of 0.678697, right? The mean of this sample, based on the mean of the sample, there is not statistically significant evidence. Therefore, there is not evidence, this is the key word, there is not evidence, this is the fail to reject the null, that the mean number of classes a student takes is anything other than 5. So we have failed to reject the null, or in this case, we have not produced statistical significance, and therefore we are left with the null hypothesis. Our conclusion is that the null hypothesis seems somewhat likely to be true, right? It's about 68%, 70% chance of the null hypothesis being true. So our conclusion is that the average number of classes that students take per semester is approximately 5. Okay, so that was our first complete hypothesis test. Let's tackle this second question and see if we can kind of get used to how this goes. So, do students get at least 8 hours of sleep per night? So notice that here our mu sub 0 value is 8. That's the number we're comparing against, the number that's in the question, 8 hours, okay. And what is the alternative hypothesis? Well, we're testing to see if students get less sleep per night than 8 hours, okay. And again, remember, we could test to see if they were getting more or test to see if they were getting less. But why don't we look at these fave stats and see if perhaps there isn't a good reason. And notice that the median is only 7.5 hours of sleep, although the max is 11. That seems nice. Somebody got 11 hours of sleep in the last 24 hours. And the minimum is 0. Somebody had to pull an all-nighter. Okay, and the median is a half. And notice that the mean is close to the median but lower, right? It's a little bit less than 7.4. So the mean is about 7.4 and the median is 7.5. And going back up here, if we're going to have the null hypothesis of mu equals 8, it just makes sense that we're going to be using the less than 8. It appears just from our cursory glance at the associations in the data, at the relationships in the data, that the average is likely to be lower. Now, that's an association, that's not scientific proof, but now our scientific proof is we're going to run the test. And notice that before, where we had pop mean equals 5, you can just tell it what it is. You don't have to put it the pop mean equals. You can just say, hey, mu equals 8. Again, it knows to expect that value from the null hypothesis. It's also the value from the alternative hypothesis, but it has to know that value to run the test correctly. Okay, so again, it's classes.column because we need an array of values to go into t-test, and that array of values is going to be the column sleep hours. Now notice the p-value at the end, we see that it's switched into scientific notation. So remember that e to the minus 15 means times 10 to the negative 15th, right? And all I'm going to say about that is it's a really, really small number, and it is approximately 0. It is not quite 0, but is statistically speaking, it is almost 0. It is very, very close to 0. So what have we learned? Okay, so in particular, it's less than 0.05, which is our alpha, right? So if it's less than 0.05, we are going to reject the null, which means that our conclusion is that mu, which is the average amount of hours of sleep per night that students get, is in fact less than 8. We are going to say that we have evidence for the alternative. Why we rejected the null? Why did we reject the null? Because the p-value was very, very close to 0, and specifically was less than our alpha. And you can see that recorded in the notebook, they have what I just said, that the average in the sample is about 7.4 hours of sleep per night, and the p-value is very small. They say less than 0.001. But again, this implies that we have evidence that students do get less than 8 hours of sleep per night. We rejected the null, and that means that we do have evidence that for the alternative, that students get less than 8 hours of sleep at night. And I do want to go back up and show you this because it's nice. It draws out the bell shape, okay? And notice that the p-value is so small, it's not visible. So let me go up and show you the bell curve, the t-distribution for the first example. So the first example where we had a very large p-value, we drew a vertical line below the mean at the test statistic, the negative 0.414. Isn't that what it was? I'm pulling this off the top of my head. I have to go back up. Yeah, the test statistic is 0.415. I guess it rounds to 0.415. So notice that we have a line drawn above the mean, 0.415 above the mean and 0.415 below the mean, and we've shaded the tails of the distribution beyond those lines. And what's the p-value? The p-value is the area under the curve that's shaded, the percentage of the area under the curve that's shaded. So again, this p-value turned out to be nearly 70%, so we can see a lot of shading. When we scroll down to the second example, the p-value was really small. Remember I said it was really, really close to 0. And yes, in truth, there is a vertical line somewhere, and I don't know how far over there, but it's way, way over. and the area under the curve, the tiny little bit of area under the curve that's out here, is just essentially 0. It's so close to 0 that we can't even tell. All right. So let's take a look at our. Oh wait, and they've got another one for us, and they're just showing a box plot of what's going on. We were testing, right? You can see that we were testing mu equals 8, which is actually at the 75th percentile of our distribution, right? So the top of that black rectangle in the box plot is Q3, which is the 75th percentile, and the bottom of that rectangle is Q1, which is the 25th percentile. Okay, and it's obviously marking the mean and the median. But notice that the mean and the median, there's a big gap between them and 8. So that is why we got such a small p-value. Okay, So it says change the question. And what do? Well, notice that they're changing the question to mu equals 7.5. So all they've done is they're doing the exact same statistical test with the exact same data, but they're changing the hypothesis so that mu equals 7.5, and we're checking to see if students get less than 7.5 hours of sleep a night. And when we run this, notice that we get a pretty small p-value. Okay. Now, why this? Okay. So they're suggesting that we take the p-value and chop it in half. And let me explain the difference between a one-tailed test and a two-tailed test. Okay. So, and I'll do it on this. Okay. So with a two-tailed test, that's when we use not equal to. So not equal to is a two-tailed test. Why? Well, because it draws a vertical line in the distribution both above and below the average. Okay, and then it shades the area under the curve that's to the left and to the right. Sorry, I actually shaded below the x-axis, sorry. And just shade this area under the curve to both sides. Okay, so what is a one-tailed test? Well, a one-tailed test is when we're testing either the greater than or the less than, sorry, that didn't turn out to be much of a less than, or the less than inequality, and we have a one-tailed test. What does that mean? Well, that means we just draw the vertical line, and this is for the less than inequality. So for the less than inequality, we draw this vertical line at the test statistic that many units below the average, and we shade to the left. Okay, so there's no shading over here to the right. It's only on the left. Now, the reverse picture, the mirror image of this picture is what's true if we have a greater than. Okay, so why do I say all of this? Well, we've cut out this area, so we've cut out half the area. So the p-value for these one-tailed tests, the p-values are 1/2 of the two-tailed test. But here's the problem. The computer is always spitting out the two-tailed test p-value. So often when we're using computers for statistics, often we run into this where it's not the p-value that we get that's the one that matters, it's half of that. Why? Because this is a one-tailed test. Okay? And notice that it makes a big difference because this is less than 0.05. The original p-value was greater than 0.05. Like, what do? Well, the correct p-value is this one because we were running a one-tailed test. So we are going to reject the null. And by the way, we sometimes write just h sub 0 rather than null. We sometimes just write h sub 0 for the null hypothesis, reject the null hypothesis. Okay? So we reject the null hypothesis. What does that mean? That means that we have evidence for the alternative, which is that students get less than 7.5 hours of sleep. So not only do they get less than 8 hours, it appears we have evidence that they get less than 7.5. Now, our p-value was much closer to 0.05 than to 0 like it was before. But we still have statistical evidence that these students get less than that these students get less than 7.5 hours of sleep. And then you can see the p-value for this specific test. We were doing less than, so there is only a vertical line there on the left, and the shading is there on the left. And you can see in writing, they're saying, hey, that's about 3.5, which is about half of our 7%, which we got when we did the two-tailed test. And you can see in the reporting out area that they're saying exactly what I just said. That we have evidence that students do get less than 7.5 hours of sleep. We have evidence for the alternative. Why? Because we rejected the null. The null hypothesis was rejected since p was less than 0.05. Okay. Again, they've drawn the box plot so we can see exactly what's going on. So now our third hypothesis test, and then we're done. Okay, do babies born to mothers who are non-smokers tend to weigh more than 118 ounces? Okay. Now we've looked at this association before, and we've seen that there appears to be a difference in the birth weight of the babies between the two groups, the smoking moms and the non-smoking moms, okay? So here they're narrowing the question down to just one group, okay? They're just focusing on the non-smokers, and right, the average weight, birth weight for the babies of the non-smoking moms is 118 ounces. That's the null hypothesis. And notice we're expecting an even greater number than that. The average birth weight to be greater than 118 ounces. Okay? And we got to get the data. Notice that we're using the births table where maternal smoker equals false. So we are getting the non-smokers. And then the NPA range we're taking the first 700 counting by 20s, from 1 to 700 counting by 20. Okay, so that's getting our sample. And now we've just calculated the fave stats, so we can see the median is 124 and the mean is 124. So it looks like that we do have some reason to believe that the mu might be more than 118. Why? Well, we see it right here from the sample at least. So let's run the statistical test and see. All right. So again, this 118 in the code block is referring to the population mean equals 118, that pop mean that was in our first test. We can shorthand it. Boom. And notice that we get a p-value of 0.0633, but this is a two-tailed test p-value. And so what do? We divide by 2. Okay. Just like before, in the second example, we're going to divide, and this p-value is less than 0.05. So we have evidence for the alternative, right? We're going to reject the null. We are going to reject the null, which means we have evidence for the alternative. What's the alternative? The alternative was that this value was greater than 118, that the average birth weight for these non-smoking moms was greater than 118 ounces. And it appears that since we rejected the null, we have evidence for this. We have evidence for that. And that's what they're going to say in the reporting out. And you can see the box plot shows you, the box plot shows you a picture of what's going on and shows you the p-value there. So that is a conclusion to our discussion of how to use the most basic of statistical tests, the one sample t-test, and how to run them in the computer and what the computer is doing. The computer is doing that probability simulation. When we call that t-test, let me get back up here, right? When we call the t-test and tell it our null hypothesis, the computer is running that probability simulation based on the t-distribution. It's running that probability simulation and reporting out a p-value. So it tells us the test statistic and it tells us the p-value. Okay, and then based on the p-value, we either reject the null or we fail to reject the null. And that's how it works. So we have evidence that the birth weight for these non-smoking moms was greater than 118 ounces on average. All right. Have a good day.